Hello, I'm Shay, and I'm going to be talking a bit about Goodstein's theorem, which I appreciate probably means nothing to you at the minute. So we're going to start off by introducing what Goodstein sequences are, and this is what Goodstein's theorem talks about. So once we've done that, we'll go on to talk about sort of the derivation of Goodstein's theorem and actually what it says about the sequences. And finally, we'll talk about why it matters, why we care about it. So let's get started with defining what a Goodstein sequence is. And in order to do so, we need to have an understanding of what hereditary base B notation is, which again is probably a new thing to a lot of people in this room, but it's not too difficult to understand. You've probably heard of base B notation before, which essentially involves writing any integer a as the sum of powers of some base b. And hereditary base B notation is essentially based on this, but taking it a slight bit further. So we've got an example here of writing 81 in base 3. And 81 is just 3 to the power of 4, so that's our base 3 notation for 81. Taking this a bit further to give the hereditary base 3 notation, all we're going to do now is write that exponent in base 3 as well. And then if that exponent had its own exponent, we'd write that in base 3. And we'd continue on until we get this nice representation of 81 using just 3's and numbers less than 3. So we've got another example here. This one's a bit more complex. It's writing the number 2021 in base 2. So you can see at the top, it's written like that in base 2. And converting this to hereditary base 2 notation, we're going to take that first term, so the 2 to the 10, and we're going to write the 10 in base 2, which would be 2 to the 3 plus 2. And then again, we're going to write that 3 in base 2. And then we get this nice representation of 2 to the 10. And then we carry on all the way through until we get this hereditary base 2 notation of the number 2021. And with an understanding of this, we're now sort of able to define what a Goodstein sequence is. And so a Goodstein sequence is a sequence of natural numbers, which there is one defined for every natural number that exists. And the first term of the Goodstein sequence for some natural number a is just a itself. And then to sort of define every subsequent term, we've got a few steps that we need to follow. So if we wanted to calculate the second term of the sequence for a, for example, the first thing we would do is write the first term, so write a in base 2 notation, because we're looking at the second term. And then once we've done that, or hereditary base 2 notation, sorry, once we've done that, we're going to swap out all the 2's for 3's. So just straight up, if you see a 2, swap it to a 3. And then the final step is to subtract 1 from that and then convert it back into a natural number, and that will be your second term, or just generally your ith term of that sequence. So we've got an example here. This is the Goodstein sequence for the number 2. So as we said, the first term is always just going to be that first number, so 2. And then to get the second term, we're going to write 2 in hereditary base 2, which of course, that will just be 2. And then we're going to change that 2 to a 3. And then finally, we'll subtract 1 from that result, and we'll get 2 as our second term. And then we'll do the same thing for the third term. So we'll go through them same steps, but obviously using different bases, and we'll get that to be 1. And then the fourth term goes to 0, and we could work out the fifth term. So if we were to go through these same steps, we'd be writing 0 in hereditary base 5 notation, which 0 in any base is just 0. Convert all the 5 to 6's, there's no 5's there, so it just stays the same, and then we subtract 1, and the fifth term would be minus 1. But we said that Goodstein sequences are sequences of natural numbers, and so because minus 1 is not a natural number, we say that the Goodstein sequence terminates when we reach that 0. So the Goodstein sequence for 2 terminates at the fourth term. And we've got a more complex example here. So this is the Goodstein sequence for the number 5. And as you can see, it grows quite a bit larger than that example we've just seen. And it continues to grow. You sort of see that it doesn't show any sign of slowing down and terminating anytime soon. And so it sort of begs the question of what happens when we go even further into the sequence, or what happens when we consider the sequence for sort of 10 or 20 or some larger integer. What happens with it? And so we notice that it grows really quickly, as we just said. And as we just said, what happens to it? This is sort of the question we seek to address. And Goodstein's theorem addresses precisely this. And so instead of just stating the theorem, I would like to use some facts about ordinal arithmetic to sort of work our way to the theorem. And so in order to do that, you might be wondering what an ordinal is. I know some people in here didn't do set theory, and so an ordinal is a new concept to a few people. And so I'll just give a very, very brief introduction to what an ordinal is. So it's a set which is well ordered by inclusion, and it's transitive. So well ordering just means there's some minimal element with respect to that inclusion symbol, and transitive means that if x is in y and y is in z, then x must be in z. And we'll also introduce this idea of a successor function. So when we have the natural numbers, if we want to find the next natural number up, we just add 1 to it. But when we're working with sets, you can't just add 1 to it. And so we have this successor function, which is the equivalent of finding the next ordinal up. So if we have some ordinal alpha, to find the next ordinal up, all we're going to do is take the union of alpha and the set that contains alpha. And with this definition, we can sort of see that maybe there might be a link between the natural numbers and ordinals. So they are often thought of together, and there's a way of defining them together. So we'll see a way of doing that now. So we said that there's a minimal element in the ordinals, and there's a minimum element in the natural numbers as well, which is 0. And so we can sort of put these together and say, okay, 0 is the natural number that corresponds to the empty set. And then using this successor function that we defined on the previous slide, we can find a way to define every natural number as an ordinal. And then using that, that's great, you've got an ordinal which corresponds to every natural number, but these are all finite. What if we want to consider something infinite, something bigger than the finite? And you might be thinking, well, we've got all the natural numbers, so surely we should have an ordinal that represents the natural numbers as a set. And we do. We have omega, which is not immediately obvious that it exists. There is a proof that goes along with it in my report, but we'll just take its existence as is now. But it essentially isn't obvious because it's not a successor ordinal. We obtained all the natural numbers using that successor function, but omega is what we call a limit ordinal. So it's an ordinal with respect to the definition. It contains all of the finite ordinals, all of the natural numbers, if you will. And this is really useful to know about. So in ordinal arithmetic, we have this nice theorem, Cantor's normal form theorem. And I'm going to slightly abuse the way I talk about it in describing it as just a base omega representation for every ordinal alpha. And this is unique. So every ordinal alpha has a unique Cantor normal form, which is sort of, as we see here, this general thing. And this is really nice to know about because it allows us to sort of go on to sort of use it. We can use this to sort of define a separate sequence which we can use to talk about Goodstein sequences and derive Goodstein's theorem. And that's precisely what we're going to do now. So we're going to define this new sequence called the gamma sequence, which is not the official term, but it's just a nice way to describe it. And we're going to define it using the Goodstein sequence. So if we have the Goodstein sequence for some natural number a, to find the ith term of the gamma sequence, all we're going to do is write that ith term of the Goodstein sequence in hereditary base I+1 notation, so just like we did when we were defining the Goodstein sequences. And then in a similar fashion as well, we're going to perform a shift of base or substitution of base, whatever you want to call it, in sort of converting all of them I+1s into omegas. And then by doing that, you might notice that we get a Cantor normal form, which we saw on the previous slide. And it's really nice to be able to define this sequence because there's a couple of observations we can make about it. So firstly, just by construction, we use the Goodstein, or the ith term of the Goodstein sequence to define the ith term of the gamma sequence. And so if the ith term of the Goodstein sequence doesn't exist, so for example, if we considered the fifth term of the Goodstein sequence for 2, which we saw would be -1, so it just doesn't exist, there's nothing to define that ith term of the gamma sequence from. And so it just simply can't exist. And there's a similar argument vice versa, which makes it an if and only statement, which is really nice to have. We also have something which is less obvious, but when you start to think about it, it makes sense. And that is that the ith term of the Goodstein sequence is always less than or equal to the ith term of the gamma sequence. And to sort of sum up why this is, if the ith term of the Goodstein sequence is greater than or equal to I+1, when we write it in hereditary base I+1 notation, we're going to have at least one occurrence of I+1 in there. And when we perform that shift of base, that's then going to go up to being an omega, which will make it transfinite. And so it's immediately bigger than any term within the Goodstein sequence. And then the equality comes from the case where the ith term of the Goodstein sequence is less than I+1, in which case when we write it in that hereditary base form, there's no occurrences of I+1 in there, and so the ith term of the gamma sequence is just going to be equal to that corresponding ith term in the Goodstein sequence. And these are two really nice facts to have because they allow us to say things about the gamma sequence which in turn we can sort of bring out and sort of relate to the Goodstein sequence. So we've got a couple of quite big lemmas on this slide, which this is a very big lemma, and I hate to state it without proving it, but in my report it's a 2-page proof and I just don't have time to go through it, so you'll have to trust me on this one. But it essentially says that the gamma sequence is strictly decreasing. So if we have a given term in the gamma sequence, if we look at the next term up, it's always going to be less than that previous term, which is quite surprising, but it's really nice to know, but it doesn't mean anything on its own. It essentially just tells us that the gamma sequence is a decreasing sequence of ordinals. So what are we going to do with this? Well, we have this other really nice fact that is a bit easier to prove, and it says that there are no infinite descending sequences of ordinals below epsilon naught. And epsilon naught, for what we need to know, it's basically the big daddy of infinities, the big daddy of transfinite ordinals. And so it says that there's no infinite descending sequence of ordinals, and we've seen that the gamma sequence is a descending sequence of ordinals, which tells us that that can't be an infinite sequence. It must somehow get to the minimum element at some point. And we've now got all the building blocks which allow us to relate this to Goodstein sequences. We saw that the gamma sequence is always greater than or equal to Goodstein sequences. And so using these facts, we can derive Goodstein's theorem, which says that every Goodstein sequence is finite in length. It reaches 0 at some point which is sort of finite in length. And this is quite a surprising result. We saw on the example of the Goodstein sequence for 5 that it seems to grow quite quickly, and that's a small example. If we look at one for sort of the Goodstein sequence for 10 or 20 or any bigger number, they grow astronomically, and so it's really surprising to find out that they eventually go down to 0. So we've got a few examples here of the length of Goodstein sequences. So as I say, we had the Goodstein sequence for 2, that was 4 in length, it terminated at the 4th term. For the sequence for 3, that was it terminates at the 6th term, and then when we get to 4, it gets really long. It's ridiculously big, and then when we get to 5, it's even bigger. And as you go up the integers, you suddenly get these really long sequences that just explode out of proportion, and so it's really cool. I think it's really cool that no matter how long they get, they always go down to 0 and they're finite in length. But why do we care about this? It's really cool, but why do we care about it? Well, there is that it's just cool. It's an unexpected result, which is quite interesting. But the main reason mathematicians are interested in it is because it's undecidable in Peano arithmetic, which I'm dropping 2 big keywords on you there. So what is Peano arithmetic? Well, it's essentially sort of the rules for arithmetic with the natural numbers. So it's axiomatized by these axioms. And essentially, if we want to prove something within Peano arithmetic, we should be able to derive it from these axioms. So what does it mean that Goodstein's theorem is undecidable? It means that it can't be proven. You can't derive it from these axioms, which again is quite strange, but it actually sort of has a proof behind it, which I outline in my report, and it essentially comes down to 2 results. So there was a consistency proof of Peano arithmetic given by a mathematician called Gerard Gentzen, and he essentially put it down to saying that if we can prove there exists no descending sequence of ordinals below epsilon naught, then it implies the consistency of Peano arithmetic. And you may recognise that. We used that to prove Goodstein's theorem, and it was actually shown by a couple of mathematicians in the 80s, Paris and Kirby, that you need to be able to show that to prove Goodstein's theorem. So if we can prove Goodstein's theorem, we can prove the consistency of Peano arithmetic, which is great, but why is this significant? Gödel's second incompleteness theorem, that's why it's significant. It essentially says that any theory, so for example, Peano arithmetic cannot prove its own consistency if it's consistent. And so if Peano arithmetic can prove Goodstein's theorem, it can prove its own consistency, and then it contradicts Gödel's second incompleteness theorem. And so this is where the interest comes from. It's an independence result from Peano arithmetic, and it's a number theoretical one at that. which is really interesting because since the publication of Gödel's incompleteness theorems, mathematicians were sort of looking for a number theoretical independence result for a long time, and Goodstein's theorem is precisely this. So that's all I've got for you. I hope you enjoyed it. Thank you for listening. And as I said, there's quite a few proofs that I omitted from the presentation, but they're in the report, so if you'd like to take a look, let me know. And has anyone got any questions?
Great, well, thank you, Jay. So, do we have any questions?
That was really nice talking to you. With this A and K, this K is one of those sequence terms, is that right?
Yeah.
Is there can you say anything about the relationship between A and K?
So I've not found any sort of links between them, but there are sort of theories which, because it grows so fast out of proportion, it's hard to make a direct link, but there are people who have identified that it's similar to certain hierarchies and certain sequences, but there's no exact way of approximating it. It's somewhere in that region.
Sean?
So if Piano arithmetic can't prove this result, what are you assuming to prove the result? Because you're assuming
yeah.
all the Piano arithmetic.
Yes, so I've taken some elements of set theory. I've essentially given a proof using ordinals based on ZFC. But essentially, Piano arithmetic would be able to prove this if it could handle transfinite induction, and it just can't.
Okay, so you result is.
Any other questions?
I was confused by your Cantor normal form.
Yeah.
Sorry, back to find it.
Have I gone too far? Yeah.
Yes, right. So why are these things unique? I didn't understand which angle. Omega seems to be omega to the 1 times 1, and also omega to the 0 times omega. So why?
Sorry, could you say it again?
Yeah, so you can write omega as omega to the 1 times 1. So your epsilon naught would be 1 and your delta naught would be 1. But you could also write it as omega to the 0 times omega. So your epsilon naught would be 0 and your delta naught would be omega. Isn't that too different?
I think the deltas have to be less than epsilon naught, because if you had your delta as an omega, then it would just sort of that would become the omega of that term. It would sort of,
So the delta should be finite.
yeah. So I mean, you could have it, but it would just merge into that transfinite term anyway, and then become a different term.
Okay.
So you said that we cannot have infinite crystal sequences that goes below epsilon 2. How about below some ordinal?
What, below some finite ordinal?
Could you have an ordinal so that we have infinite crystal sequences below it?
So definitely not below epsilon naught, because that would just be sort of a subsequence of that one below epsilon naught. I believe it's beyond the scope of the project, but I believe there are other epsilon numbers greater than epsilon naught, which I have not really looked into, but I'd imagine not, because then it would contradict the well-orderedness of ordinals.
Yeah,
So if you have that table of how long before it comes back to 0. Okay, and for 4. So is that a precise answer? 3 times 2. Is that the exact? That's the exact answer.
Yeah, which is really nice.
And weird.
Does that mean someone's actually done that many calculations, or is it a more complicated proof to derive?
I don't know.
that?
I'm not sure.
Well, clearly not that computations.
Do they keep growing, or are there
They
some
keep growing.
bizarre
Yeah,
numbers where
it
it's suddenly
goes
small
really
again?
large. And actually, although they were developed for this purpose of showing a independence result for piano arithmetic, there are actually links to other areas which you wouldn't expect. So a few years after the unprovability paper, one of the people, I think it was Paris, who was involved in that, he went on to write a paper a few years later about how it could be linked to a dynamical system, which is not naturally occurring or anything, but because of the rapid growth, they seem to think it might be somewhat relatable to the growth of the universe, which is quite nice. I think that's quite cool. I didn't look into it, but it seems quite cool.
Great. Okay. Does anyone have anything quick to ask? Yes. Thanks, Shay, again.
Thank you.